Hi everyone, and welcome to yet another virtual chemistry lesson in thermochemistry, where we are going to talk about the concept of chemical energy, what that means, and also introduce the concept of enthalpy and calorimeters. So, you probably noticed by now that in some chemical reactions a lot of energy is released from the system to the surroundings. For example, light, heat, and sound can be transferred to the surrounding during, for example, explosions or various types of combustions and reactions like that. Here's a sample reaction for you. It's the thermite reaction, where you have iron 3 oxide reacting with aluminium to form iron and aluminium oxide. This is a reaction that you can see on the picture to the right that also gives off a lot of energy to the surroundings. In fact, there's a hint for that, and that is in the states of matter of the products in this reaction, where you can see that we have liquid iron and a liquid salt being formed. So a lot of energy is released in order to make salts and iron melt. This is a reaction that can reach about approximately 2400 degrees Celsius. So it's a very dangerous reaction and was used to spot weld various types of things in hard to reach places. And as you can see in this reaction, it's not just heat being given off, it's also light being given off, and you probably hear a sparkling sound. So there are different types of energy being released here, but we'll assume that it's mainly heat being released to the surroundings from the system. Now you'll have to excuse my poor drawing skills, but here I have a drawing of a beaker in which we've added 2 white salts. So this is supposed to be a pile of salt then, which is solid barium hydroxide and ammonium chloride. So if we mix these 2 solid compounds, and you have the formula for them here, the following reaction happens. I've added water crystallization here because that's how we find the most common version of barium hydroxide. And then we add ammonium chloride. And just by having these two mixed together as solids, they will start to react with each other to form ammonia gas, water, and barium chloride. As water is formed throughout the progression of the reaction, this will turn into a slurry, and then this will be a sort of liquid solution, a water solution. And this is a reaction that reaches about minus 20 degrees Celsius and is a fairly fun demonstration. We don't have barium hydroxide at my school, so I can't give you a demonstration myself. But if you search for endothermic reaction barium hydroxide ammonium chloride or something like that on YouTube, you'll find lots of nice demonstrations showing how you can freeze water with this chemical reaction. So, chemical reactions can either absorb energy to the surroundings or absorb energy from the surroundings or release energy to the surroundings. And to explain this, we need to think about what actually changes during chemical reactions. What's the difference before and after a chemical reaction? Here's a sample reaction where you have hydrogen gas reacting with oxygen gas to form water. What actually changes here? Well, we have different bonds before and after the reaction has taken place. Before the reaction, we have bonds between 2 hydrogen atoms here, covalent bonds, and we have covalent bonds between oxygen atoms. But afterwards, we have covalent bonds between hydrogen atoms and oxygen atoms. So there's a difference here. And this is important. Chemical energy is stored in the chemical bonds. Remember that the chemical bonds in turn are electrons. So dependent on how the electrons are arranged, we'll have different amounts of chemical energy stored. So the changes in chemical energy, which can be increases or decreases of a substance, corresponds to changes in the chemical bonds. So change in chemical energy equals change in chemical bonds. All right. So, and this also explains a little bit why covalent bonds are formed. And that some elements we find are found as diatomic molecules. So, for example, let's look at elemental hydrogen. It's found as a diatomic molecule. And the explanation for this is the reaction between hydrogen atoms. Here you have two single hydrogen atoms with their free electrons. And once they react, these two electrons that are shown as dots here in these loose structures are within this bond then. So they're shared this way. When the hydrogen atoms are on their own, they have not reached no gas configuration, which means that they're in a unhappy place, which is a high energy state. But when they react, they create a covalent bond, share electrons with each other, and thus reaches a noble gas configuration. That causes them to become more stable, which corresponds to a lower energy state. So there's a difference between the high energy state before the reaction and the low energy state after the reaction. What happens to that energy? Well, it's released to the environment as heat, among other things, but we'll assume that it's mainly heat right now. So we find hydrogen, for example, including other small elements, as diatomic molecules because when there's one hydrogen atom, there's typically another, and they will react spontaneously to form a more stable version of hydrogen. So, due to the fact that we always have more than one hydrogen atom, or typically in one place, they will come together. And the hydrogen atom is rather reactive, and if there wasn't hydrogen there, it would probably react with something else. So, when new chemical bonds are formed, there are two things that need to happen. So here we have the reaction for the combustion of water, and I've written the same thing with structural formulas below here, structural formulae. So we draw out the covalent bonds. Okay, the first thing that we need to do in order to form these water molecules is to break up these bonds within the previous molecules. So that's the first step. Bonds need to be broken. In order to do this, we need to add energy. In order to break something, we need to add energy. Imagine that you have a brick wall in front of you. In order to break that down, you need to apply quite a substantial amount of energy using a, for example, sledgehammer. The same applies for chemistry. In order to break something that's formed, you need to first apply energy. But then, new bonds have to be formed after the chemical reaction. And as I showed you before, the formation of new bonds happens due to the fact that atoms want to reach a noble gas configuration. So they combine together because that would result in a lower energy state. So therefore, energy is released to the surroundings. So we need to form new bonds, and this process causes atoms to come closer to a noble gas configuration, and that will then release energy from the surroundings. When we have energy in the system increasing, we write that as a positive number. And when the energy within the system that we're looking at decreases, we write that using a negative number or a negative sign, just to indicate the direction of the energy. A positive energy corresponds to an increase in the system's energy. A negative corresponds to a decrease in the system's energy. All right. We can use the fact that energy being increased and decreased during the formation and breaking of bonds corresponds to chemical energy. We can use this to do calculations and try and estimate if energy will be released in a reaction or taken up. So then we can talk about the concept of bond energies. The bond energy is the energy required to break up 1 mole of a specific type of bond of a substance in the gaseous state. It's not a perfect concept, as the general structure of molecules also affect the energy within bonds, so not just the bond itself but also the neighbors around the bond will affect the stability of it and therefore the energy stored within it, but still it will allow us to predict changes in energy during chemical reactions. And this is something, of course, that we can determine experimentally and then build on our experimental models to build theoretical models. And this has been done, and data has been collected in huge tables such as this one. Here we have different types of bonds and the energy, the bond energy, so the energy required to break 1 mole of a specific type of bond. For example, in order to break a carbon-carbon covalent bond, we need to apply 347 kilojoules per mole. Because the more we have, the more energy we need to apply. If we have 2 moles, we need to add twice this amount. 3 times, then 3 times. So it depends on how much we have, the more energy we need to add in to the system. But still. And here we have bond types, bond energies, bond types, bond energies, and so on, for quite a few different bonds. And this is for molecules and covalent bonds that we use this concept. So, how can we use them to predict energy changes during chemical reactions? Well, we have a nice formula to use, and it looks like this. The delta H, so the difference in H, and I will come back and explain this later, equals the sum of the delta H of all broken bonds. And remember, to break bonds, we need to add energy to the system, so this is written with a positive sign, plus the sum of the delta H of the formed bonds. When bonds are formed, energy is released to the surroundings, so this is written as negative. And delta H, if you look at that, then we go back, you see this is the symbol that we use for the bond energies as well. What this actually means, I'll try and explain a little bit further into the video, but it's a measure of the change in energy content of a system. And I will try and explain that soon. Let's do an example for now, though. How much energy is given up or taken up when 1 mole of hydrogen gas reacts with 1 mole of fluorine gas? Here we have the reaction for the reaction between, so the reaction formula for the reaction between hydrogen gas and fluorine gas. And of course there should be a G here in parentheses to indicate that the product is formed is in the gaseous state as well. Actually, let me do that real quick. There we go. Because this concept only applies when we're working with substances in the gaseous state. So, when I like to work with exercises like this, I'd like to make a table just to keep track of all the numbers I have to use. So, first and foremost, we knew from the exercise on the previous page that we have 1 mole of hydrogen gas reacting with 1 mole of fluorine gas. We can use this information and our knowledge about molar ratios to predict that 2 moles of the product will be formed. Right. Then the next step would be to write down the structural formula of the molecules. We can do that like this. Very basic, simple molecules, because this is me introducing a new concept to you. Right. Then we can write down how many bonds do we have per molecule. Again, simple molecules. We only have 1 bond per H2 molecule, 1 bond per F2 molecule, and 1 bond per HF, so 1 bond per hydrogen fluoride molecule. Okay, then we can sum up how many bonds do we have in the actual chemical reaction, right? So each molecule contains 1 bond, and we have 1 mole of molecules. So multiplying the number of bonds and how many molecules we have per molecule will give us the total number of bonds in the reaction. And that's what I do here. 1 mole multiplied with number of bonds per molecule equals the total number of bonds in the chemical reaction here. So we have 1 mole of HH bond, so a hydrogen covalent bonds between hydrogen atoms. We have 1 mole of covalent bonds between fluorine atoms, and we have 2 mole of bonds between hydrogen and fluorine here within the hydrogen fluoride. All right. The bond energies can be found in the table. For the HH bond, it's 436 kilojoules per mole. For the FF bond, it's 159 kilojoules per mole, and for the HF, it's minus 565 kilojoules per mole. And this is important. Remember that here we need to change the sign of the energy because energy has to be released when these bonds are formed. And this amount of energy being released equals the amount it would take to break them, but we just change the sign. So it's a negative sign for the new formed bonds instead. And then we can easily calculate the energy required to form or break bonds here within this chemical reaction. We take the number of bonds, multiply with the energy per mole of bonds. So we take these two, multiply with each other, and then we will get 436 kilojoules per moles of H2F H bonds. So this is the total number because we only have 1 mole. We do the same thing here. We take these two squares, multiply with each other. The energy required to break 1 mole of bonds multiplied with the number of moles of bonds we have. Again, it's 1 times the number, so it's the same number. And here we have 2 moles being formed due to the molar ratios here. So we need to take 2 moles, multiply with this negative value to get a total of minus 1,130 kilojoules. All right, now we know the energy, the sum of the energy with the required to break all of the bonds. We sum that up for the hydrogen bonds and the fluorine bonds. And we add that together with the negative value of the energy released when all of those bonds are formed. And then we get a delta H of minus 535 kilojoules. Note that the value we get from this is a negative value. That means that the reaction gives off energy, because a negative sign in thermochemistry indicates that the energy flows from the system to the surroundings. If we were to do a calculation like this, and we got a positive value of delta H, then the reaction would take up energy instead, and the energy would flow from the surroundings to the system. Okay. Delta H then, what does it actually mean? Well, we don't talk about heat very often in chemistry. We like to talk about enthalpy. And enthalpy, I'll try to describe it using some examples, but it can be described as the heat content within something, the potential to give off heat. And you can think of it as the sum of the available chemical energy that's stored within the bonds and the current heat energy, which is related to temperature. The symbol for enthalpy is the large H, and the unit is joules, because this is just energy. It's just different types of energy that we're talking about. Experimentally, we can only measure changes in enthalpy, for example, the change in enthalpy during a combustion process. And whenever we talk about changes, we usually write a big delta, and when we talk about changes in enthalpy, we write delta H, like this. So, how does heat and enthalpy differ from each other? Well, hopefully this will clear it up for you a little bit. Here I have a picture of a beaker of ethanol in room temperature. The ethanol has reached room temperature, so it doesn't really give off much heat at the moment. We have the temperature of the room and the temperature of this. It goes back and forth here, but they've reached a sort of equilibrium. They have the same temperature here. However, Even though it doesn't give off much heat at the moment, it has a very high potential to give off heat because a lot of energy is stored within the chemical bonds of ethanol. So I transfer this to a crucible because I don't want the glass to crack, and then I ignite it. Let's see what happens. So look here, we have about 20 degrees, so current room temperature. When I ignite it, it starts to burn and it gives off a lot of heat. And this heat has to come from somewhere, and it comes from the chemical energy being converted into a lot more of heat energy. We have a change in enthalpy because energy is released from the system to the surroundings. But now we have a lot of energy here, and it's not just related to the initial heat we had, but also the heat generated from breaking the bonds and forming new bonds. And we need to take into account both the starting heat, so the temperature which this mixture is at when we start, and then what happens when the chemical bonds are broken. So even though it wasn't very warm, it was just 20 degrees warm, it had a lot of potential to give off heat. So it had a lot of enthalpy in total. We cannot, of course, measure the total enthalpy it had, but rather we can measure how much enthalpy is being released as this reaction progresses. So hopefully that cleared up the difference between ability to give off energy and the heat energy it has from the start. There are two cases where two types of changes in enthalpy we can observe, and the first one is endothermic. And endothermic reactions, they are the reactions where enthalpy of products is higher than that of the reactants. That means that the energy has to be transferred from the surroundings to the system. And delta H then will have to be positive because the system, if it acquires more energy, then that will have to be a positive value if we follow the convention that we use. A typical example of this is photosynthesis, where carbon dioxide and water are combined using light energy, so we add energy, and therefore we can write that on the reactant side to form glucose and oxygen gas. The small molecules in the beginning here have a rather low enthalpy, whereas the products formed in the reaction have a high enthalpy. If we want to illustrate this concept, we can write an enthalpy diagram like this. On the y-axis, we have enthalpy, and on the x-axis, we have the reaction progress, so essentially time. Reactants, we can write them at a certain value. We don't have a value for this, but this is just to illustrate the concept, right? So we don't know this, but we know that when these are combined, energy is taken up via sunlight in a smart arrangement within the leaf of plants to form products with a higher enthalpy. So we have an increase in the energy content of this system as new molecules are formed. Energy has to be taken up, so the delta H is positive. Whenever the products are higher up in a diagram like this than the reactants, we know that it's an endothermic reaction. Okay. Exothermic reactions, that is reactions where the enthalpy of the reactants are higher than those of the products. That means that energy will be released to the surroundings from the system. The sign then will be the opposite of the endothermic reaction. In this case, it's written as negative to indicate the flow of energy goes in the direction from system to surroundings. Typical examples of exothermic reactions include combustion processes of various types and neutralization. And we can look at the one that was demonstrated previously, the combustion of ethanol. In this case, energy was released to the surroundings. The surroundings were heated up, and therefore we can write energy as a product here, though you can exclude the question mark unless you're especially enthusiastic. If we were to draw that in a diagram, okay, in this case I see that I have a different chemical reaction. The combustion of hydrogen gas, where hydrogen gas and oxygen gas react. That's also a reaction that generates heat, and therefore the products, that energy has to come from somewhere. That comes from the chemical bonds. That means that the products will have less energy stored in their chemical bonds and will be further down in a diagram like this. So whenever the products have a lower enthalpy than the reactants, energy has to be released to the system, and that's written with a negative sign. There are ways for us to experimentally determine enthalpy changes. For example, we can use calorimeters. That's an instrument for measuring heat changes then. It could look like this. You could have some sort of insulated container containing a reaction mixture in an aqueous solution. So water solution, and we have things in the water solution that react. We have a thermometer attached through here to measure how much energy will be absorbed or released. And then we have an insulated lid, so we try to have it as a closed system as we can here. Because the reaction is taking place in water, the water will either take up the energy that's released or have to give the energy to the particles that react, in which case the temperature of the water will decrease. So if the value on the thermometer goes up, it increases in temperature, then we know it's an exothermic reaction. If it's an endothermic reaction, the value will decrease, so to speak. So that's one way to measure the heat given off, and this can then be related to enthalpy, and I'll show you how in just a moment. But this is for reactions taking place in aqueous solution. You mix them, everything's insulated, and you measure the temperature change. There's also calorimeters for measuring heat changes during combustion processes, for example. Then you could have a setup looking like this. You need to have some sort of draft shield here to make sure that we don't have any air blowing in and out of here. We have a burner with the fuel that we want to investigate, because we're talking about combustion, something has to burn in oxygen, right? Above this setup, we hang some sort of high conductivity container. For example, it could be made from copper, which will conduct a lot of heat very easily, so we don't lose much heat from this flame to this water because of the material in between them. This container just contains water with a thermometer and an insulated lid like this. If the water's temperature is increasing, that's because, of course, the fuel is burning. So and then we can measure exactly what we had before we started igniting the fuel, and then where we end up at afterwards. Then we can also determine the mass we can extinguish this flame. We can have the mass of this before and afterwards. Then we know how many grams of fuel that have been burning, and that can be related to how many moles of fuel that have been burning. And this can then be used to estimate enthalpy changes as well. So how do we do this? Well, if we use insulated calorimeters like this, where water is heated up, we can make an assumption. And that assumption is that the heat that is taken up by the water corresponds to a change in enthalpy of the reaction. And we can then assume, if it's well insulated, that there's no loss of energy between there. That we assume that all of the heat taken up corresponds to energy released by the system. Then we can use the formula for heat that we had before, but we can instead add the delta H here then. And that has to be negative or positive dependent on what we do. So where the in this case, since water was the surroundings that was heated up or cooled down, then we can use the specific heat capacity of water, which we know. We know the mass of the water we had, and we know the temperature difference. Then we can estimate the enthalpy as well. And that will be a negative sign, of course, because if the water increases in temperature, then the enthalpy has to have a negative sign. So let me fix that as well. Always something, but there we go. So the heat taken up by the water multiplied by the mass of the water and its specific heat capacity will correspond then to the approximately the change in enthalpy. And this is if it's an exothermic reaction. Then the temperature will increase. Of course, this is an assumption that no heat is lost between the reaction and the water being heated up. But of course, there's no such thing as a perfectly insulated container, nor is there such a thing as a container with a perfect conductivity. So some energy will be used, but we can make rather good assumptions using this method and calorimeters. And then I'll just end off by speculating on the name calorimeter. Because you've probably heard of calories, right? When you talk about food, the energy content of food is given as number of calories. And joules, which we use, for example, in chemistry, can very easily be converted to calories instead. It's just a different measure of energy, and the energy content of food is determined through calorimeters. Of course, a little bit more complicated and well-designed calorimeters than I have tried to draw here using PowerPoint, but that's where the word calories come from as well. So, I hope you've learned something today, and I will see you in a future video. Thank you for your attention.